Welcome to Rubber Duck Engineering, episode 99. This week, we are starting our exploration into machine learning, and we're going to try to build a machine learning algorithm for contract bridge bidding. Whoa, Eric, how are you?
I'm okay. So many people are sick, but I'm okay.
Yeah, I hear you. There's a lot of that going around.
There's a lot of that going around. At least where we live in California, there's a lot of that going around. But yeah, things are okay. We had some technical difficulties before the show, which is why we're a little late. And there may still continue to be some technical difficulties, but we'll get it sorted out.
All right, welcome to the show. We were planning to screencast from my machine, but we learned that my internet upload bandwidth is not strong enough to both screencast my beautiful face and my Visual Studio Code window. So we're trying to get Eric's machine up and running with all this stuff.
Yeah, we have different projects sort of catch people in different ways, and this project has really captured Dr. Barth, which is great. But so he has flown ahead several miles.
Hi, Anyhow, welcome. Yeah, I wanted to do like machine learning things for a long time, but I've been sort of intimidated by it, and I haven't been sure like how to start or like what to do. And so I was reading through like the TensorFlow tutorials, and I was reading the manual, and then this bridge project I thought was actually a good starting point because it turns out the show is not the first time that Eric and I have hacked on projects together. We many years ago, actually back in 2015, we did a bunch of work on a different
earlier,
even earlier, on a different bridge bidding AI. So we did that one based on the Z3 SAT solver from Microsoft, and so that's like you program a bunch of logical expressions about like what bids you ought to make, and then it tries to like solve the equation and produce the correct bid for you. Oh yeah, WebAssembly is super awesome. That's another. We were actually thinking about doing a WebAssembly interpreter on the show. That was one of the ideas we were kicking around. So we have a sort of history with Bridge. So if you're not familiar with the game of Bridge, it's a card game. It's played in teams. So you have two teams of two players, and you deal out all the cards to those players. And the game proceeds in two phases. So in the first phase, you look at your hand, and you try to negotiate with your partner how many tricks you're going to win in the second phase of the game, and also what suit should be trump. And then you're not allowed to like talk with your partner in English because that would be too easy. Instead, the way you communicate with your partner is in this very restricted bidding vocabulary. So you might say like 1 heart, and what that means is we're going to win one more trick than 50%. So if you deal out the cards to 4 players, each player gets 13 cards. So 50% is like 6. So 1 heart is like, we're going to get 7 tricks in the trump suit of heart, if the trump suit were hearts. And then it sort of goes around the table, and you can keep like raising the stakes, like bidding higher and higher numbers. And then whoever bid the most, they become what's called the declarer, and they have to then prove it in the second phase, where you actually like play cards in your hands and capture other people's cards and stuff. And so the part that I found interesting for a long time is that first phase. Like, how do you communicate with your partner? How do you negotiate with them and figure out what how many tricks you're going to get? And the way the scoring works is you're sort of incentivized to get to certain levels. Like if you get like four hearts, that's way better than getting 3 hearts. But 5 hearts is not that much more than 4 hearts. And so these sort of natural places you try to get to in the bidding. So then I thought, well, why don't we try it with machine learning? So to start on a machine learning problem, you kind of need a data set. And so the first question we had to solve is, where are we going to get the data to train the model
on? I've been a little distracted trying to fight with our technical difficulties, which is why you've been solo casting here.
Have you succeeded in solving your technical difficulties?
No, we're in deep technical doo-doo, but that's okay.
All right, I'll keep talking then.
No. I'm not going to be able to solve it by ourselves. We're going to have to fake it. But yes, where do we get the data set? Well, you found a data set via BBO.
So what is BBO?
BBO is Bridge Base Online. a random company in Utah or something, like from the 90s, and it still looks like the 90s. No. Yes, maybe I'm throwing shade, but I shouldn't be throwing too much shade. Bridge is sort of stuck in a time warp, honestly. There are a few people who are like our age, who I guess we're old now, but even when we were young, we were young for the Bridge scene, and I still think we're young for the Bridge scene because I'm not sure there was a scene after us.
I think that might be the case. So, but anyway, it's a website where you can play Bridge with other human beings online, and we found through various shenanigans some like backward, you know, I don't know if it's a backdoor really, but like a very rarely visited page on their website where you can download transcripts of games. And so I wrote a very polite script that would every few seconds go and ask for one more, please, and downloaded about 20,000 different basically records of tournaments that they've run. And so I don't know what the skill level is of players in this data set, but probably better than random. And so that's sort of the basis. Polite, yeah. Well, I didn't want to hammer their server and get blocked, right? Like I got the sense I wasn't really supposed to be using this part of the website, but it was public, so I don't know.
You were clearly not the first to do it, by the way. There are other blogs that talk about people doing this.
Yes.
And since you had to go to sleep to get your script to finish, it was quite polite on modern internet standards.
So anyway, so that netted out to about 500,000 plays of Bridge. And so then we tried to build a model. So do you want to share your screen and we can see what we got?
I also learned in our technical difficulty setup that I had been letterboxing my screen terribly for the last, probably 50 episodes. So I made it bigger for everyone.
So where are we in the technical difficulty? What does...
I think I haven't stared at it quite enough because it's really difficult to debug these things while also trying to talk. But I think the Python inside my virtual env is funkified. Oh, no. I can seem to run Python outside. I think when I go inside...
I see. Should we switch over to trying to screencast from my screen? Even if I'll sort of get laggy in my video, but maybe that would be better.
That may be better. I mean, we can walk people through. I just don't know we'll be able to run TensorFlow.
Okay.
When I try to run it, it sort of gives up.
Okay, I'll try screen sharing, and then if my video gets horribly laggy, just let me know, and we'll find another solution here.
All right. Please stand by.
Please stand by for a screencast rearrangement. Okay. So the first thing we need to do is read in the data set. So we found another open source project called BridgeBots that had been down a similar path to the path that we were heading down. So they had a parser that was able to read in these files that we downloaded from BridgeBase. And so we got their parser wired in. And then what this thing does is basically reads in all the files in this data set, parses them using their parsing algorithm, and then sorts them and dumps them back out.
Can you show one of the Lin files? They're nutty.
Let me just add a folder to my workspace here.
The reason why we had to go find someone else's parser is because the BBO proprietary format, which is text, they don't publish the format for it. And, 4 other people, which is probably a lot in the Bridge scene, no offense, shade on the Bridge scene, had written parsers for it. And we tried several, but we did finally find a modern written one in modern Python that someone had updated in the last few months that seemed to do a pretty decent job. Because these files are nutty.
So here's an example of a file. So this is like the beginning of a game record. Oh, wait, we have a comment here. Nice to see poetry. Yeah, poetry has been really great. Like it's, I wrote a lot of Python like 10 or more years ago, and Python has like advanced tremendously in the last 10 years.
Yeah.
And poetry is way better than a previous thing.
Yeah, but I still don't actually fully understand. I like the PG bar, I think, is like the end of bidding marker.
Something, but this represents the hand, right? So this is like you have a 1 of spades. Oh, this is spades. You have an ace, a 4, and a jack or something, and then I don't know, these are the cards somehow, and then this is the bidding history. So like somebody bid 1 no trump, somebody passed, then they bid 2 spades, pass, etc. And then over here, this is all the cards that got played. Like somehow somebody I think played the 3 of spades, and then the jack of spades, and the ace of spades, and then eventually the game was over. So I mean, you could write a parser for this, but fortunately, there was one that was already written that we could use.
Yeah. So we pulled in their parser.
And then parsing was really slow because we're parsing a huge data set. And so I parsed it once, and then I used Pickle to dump out the parse representation into just a file. And I actually made 2 of these files. I made one that had all 20,000 records, and then one that just had the first 1,000 records, because even reading in Pickle format was pretty slow. And so then
we could optimize their parsing format is possibly more verbose than we would need, and I bet we could optimize it down into something that would pickle tighter and read and load faster. But
yeah, so like to give an example, like let's look at the 1K files here. So if I run this thing, so this is just a thing to read in the pickle format, do some very basic analysis of like what bids were made and what contracts were made, just to basically see, is this data set sane?
Mm-hmm.
And the data set looks pretty sane. Like there's a huge number of passes. So this is just the very first bid. So the dealer is the first person who gets to bid, and we're focusing in to simplify the problem at the beginning about just like what happens for the very first bid. So a lot of time, the first person passes, which basically is the first person saying, my hand's not that remarkable. Maybe somebody else has a more, ace and king and queen filled hand that will dominate the play part of the thing. And then there's a bunch of like opening 1 level bids, which is kind of normal. And then 1 no trump is pretty popular. And then as you get higher, they get less and less popular, which makes total sense. And then these are the final contracts that people arrive in. So like 1 no trump is a very common contract. By the way, if you don't think the person bidding is going to make it, then you double them, which like doubles the stakes. It's like haha, you're not going to do it. But then if they think they're really going to do it, they can double you again, so they can redouble and be like, no, it's really happening. Anyway, so those are pretty rare, as you see. But then you get some decent contracts. Like you get all the way up to like a bunch of like, the most you can bid is 7 of something, which basically means we're going to win all the tricks, right? Because 7 plus 6 is 13, and that's the total number. And so it was all sort of same.
So somebody ended up in 7 no trump doubled.
Well, this is just if I go to the 20,000, which is the full data set we have, there's some really amazing things you end up in. So I'll just show you how long that takes to so most of the time here, just to load in this 20,000 data set, which is 600 megabytes, by the way.
For context, those who haven't played bridge. So in bridge, the bidding, you end up negotiating over a trump suit. And that's the suit that if you've played spades, it's another card game, or there's other games that have trump suits. It's like the suit that's more powerful than all the rest. Maybe you covered this earlier while I was in technical difficulties land.
No, but basically the trump suit means if you play a trump suit on a trick, then you're going to win that trick. So if you have like the ace of trump, that's awesome because it always wins. Firefall does not need to be loaded at once. Like if I was smarter about using TensorFlow, they have a streaming mode that I don't know. I literally never used TensorFlow before, so I'm just doing everything the most basic way possible.
But so anyway, so bridge has like an arbitrary ordering, preferential ordering of which of the suits is like higher than each other in the bridge or in the bidding, and it's clubs, diamonds, hearts, spades, and then higher than that at a given level is no trump, which means I don't even need trump. I'm going to be able to do what I said I'm going to do without using trump. And so 7 no trump is the highest bid. And so to get to this, where some person's saying, I'm going to take all the tricks, no matter what you do, and then someone else is doubling them saying, no, you aren't, is a very strange situation to be in.
Well, I don't know, this is taking forever to load, but when we actually get the full data set with all the 500,000 tricks, there's a 7 no trump redoubled, which is completely ridiculous. It's like,
Like
I don't know.
someone
They
did
just got
something
really
wrong.
mad at that table. Like, no, I'm going to take all the tricks. No, you're not. Yes, I am.
Because 7-no trump is like super easy to reason about.
It's like, do you have an ace? In which case, you're like, the other person's not going to make 7-no trump. All right, this is taking too long. I'm just going to cancel it. Okay, so then the next step was to actually build a model. So here we're importing TensorFlow, just looking at the 1K things to start with. And this is the whole model. So you're laughing.
It's just, it's funny looking through, again, we're both approaching this never having used TensorFlow or any ML before. Well, okay, fine, like little tiny, tutorials or whatever. And I was just amused at the TensorFlow docs, which like cite which research paper each class came from. And I was like, okay, that's a whole different thing. And then I'm just amused at like that they've teched up to infinity in terms of, 4 lines to construct a model, but have not teched up to infinity in like explainability or usability. But
well, that's why I felt the whole thing was sort of like unapproachable, or like I was afraid of it. And like I had the same thing in other things where like there's some domain that I didn't know anything about, and it seemed really mysterious. And then just doing some basic project in that domain, you realize, okay, it's just a bunch of code that fits together, just like every other domain is a bunch of code that fits together. And so once you figure out how to plug their things together, then you can do sort of basic things.
And this is, we were talking about this last week on the show about starting and how many people, I think schools often and working in large companies doesn't teach you how to start often. And I think starting is so important because you just start and you realize that it's not as bad as you think, at least for me, because
I always get the same thing, like writing the script that politely downloads the data, like.
What'd you say?
I just like this. Starting involves a lot of the same things, like writing a little Python script that like hits a web server and like pulls down some stuff, and like it's all the same stuff. So I can talk through this model, what this is doing.
Sure.
So this is just taking one hand. So this is the dealer's hand of 13 cards, and it's trying to predict what is the first bid that the dealer is going to make. And so you present the input to the model. Like obviously TensorFlow doesn't know anything about cards, but it knows about integers. And so the input to the model is just a list of 13 integers where we've assigned one integer for every card in the deck.
And so that input class is a spec. It's like describing what your input's going to look like.
Yeah, this is like the type declaration of the input. Later on, we'll actually feed it the actual data that we have. But this is just saying, I'm going to give you data that is 13 integers.
And I think you said last night, this part is optional. Like TensorFlow will like figure out types for you, but this way you get like better error checking when you do it.
Yeah, there are a bunch of different modes. This is called the functional API, which just made sense to me, and so I did it this way. But there's like the sequential API, and there's even like a lower level that you can work in or whatever. But this just seemed like the simplest way of doing it.
Okay.
And so now machine learning is all about floating points. So you have to somehow get your integers out of integer land into floating point land. And so they have this layer called a category encoding. So what this is doing is it's taking as input this list of integers, and it's going to produce as output a vector of floating point numbers. It's going to produce 52 of them. So it's going to output one floating point number for every card in the deck. And then the floating point numbers are either going to be 0, meaning that card was not in the player's hand, or it's going to be 1, which says, yes, that card was in the player's hand. And so it's taking these, basically interpreting the integers in this list as indices into this array, and then turning on the bits in the array that correspond to whatever was in the list.
And that's what category encoding does?
That's what category encoding does. Apparently, this is a common thing to have a like list of indices that you then want to turn into zeros and ones.
Sure.
And you can obviously customize it. You don't have to use 0 or 1 or whatever, but 0 and 1 is the default.
I see. So category encoding is like a helper function that takes an int and turns it into one of n floats.
Correct.
In a tuple.
So, yes, there's apparently a very normal thing in machine learning. It's called one-hot encodings, which basically means 1 means yes and 0 means no. Okay. So this is multi-hot meaning I can turn on as many of the entries in this vector as I want. I don't have to only turn on exactly one of them.
Speaking of starting, that's another thing about starting, is that it's a different activity, and that it is a lot of like vocabulary learning and other such things.
And you often just like, for a while it's just abstract. Like I was reading their docs around the time, one hot, one hot, one hot. I was like, okay, that's like the 10th time they said one hot. I went to Wikipedia. It's like, Wikipedia, what is one hot? And Wikipedia was like, oh, here's what one hot is. Like, okay, that makes sense. Now I can contextualize all the things that they were telling me before. Same thing with this crazy ReLU thing. Like the 10th time they talked about ReLU, or I don't know how to pronounce it, in their docs. I was like, okay, Wikipedia, what is this? And it turns out what this is, it's just a function that for all the negative numbers outputs 0. And for all the non-negative numbers just outputs that number. So it's like a line that goes across and then starts going up diagonally. That's all it is. Like it's nothing totally fancy. It's just that.
I'm trying to think of other domains that like shed their jargon. Because my
it's really
limited
hard to shed jargon.
What did you say?
It's really hard to shed jargon.
But it happens eventually. It's like a generational thing. And this happens with English too, or with not the English, with languages, right? That languages sort of change in a generational fashion. And I just don't think the third generation of ML programmers are probably going to use this same jargon, because it's a needless learning cliff.
Yeah, it's clear this thing was like built by super experts. It's clear the super expert got bored of doing the same thing all the time, so they created this thing to automate the thing they're doing all the time. But these people are still like super experts who are like steeped in the research lore of all this stuff. And there's got to be a version of this for like people like us who just don't know, have no idea what we're doing, who just want to slam junk together and have it work.
Well, as I was saying, I looked at the TensorFlow docs right before, and they were having research citations, which is great. I didn't care. Like that wasn't approaching me. And then I look at the PyTorch docs, and the PyTorch docs greet you with latex diagram or LaTeX diagrams. It's like, that's great too. Also not what I'm looking for.
Clearly you're too smart for me if you're talking to me in LaTeX. Anyway, let's keep going through the model.
Yeah.
So this, so far we haven't had any trainable parameters. So everything we've been doing is completely deterministic, and there's nothing to learn. So all of the learning is going to happen in these next layers. So these next layers have a bunch of hidden values in them that just get initialized to random things. So what this does is it takes the 52 floating point vectors as input and produces a vector of 16 floating point numbers as output. And the way it does that is it just multiplies a matrix with these tunable parameters, adds in a bias vector, which is just another vector, and then applies this ReLU function at the end. And then did this again for no particular reason. And then I said, okay, when I actually want output from this model, I want one slot in my vector for every legal bid that exists in Bridge.
So let me play this back to you, because I have an understanding of ML that may be wrong, but I just want to validate. So my understanding is that ML is this: you define your inputs and you define your outputs, right? So at our top level, we're going to give you a 52 unit by 1 unit matrix.
Mm-hmm.
That's our input. And our outputs, we're going to want whatever the length of legal bids is.
I think it's 68 or something.
But it's 1 by 68. Again, they're all floating point numbers. Outputs. Is that correct?
Correct.
And then the inner layers are typically hidden in this way. Like this is what the ML model, this is what the ML training does, is like fill in values in these inner layers. But they're all generally fully connected, right? So you have, in this model, you have 13 nodes in the input, and then you have 16 nodes in the first layer. And each one of those 13 nodes connects to each of the 16 nodes with a bias, I think they call it.
Well, with a weight and a bias, yeah. With
a weight and a bias. And the weight tells how much of that 1/13th value of each one of those 13 values propagates to each of the 16 values. With what weight? So like, say it was a 1 in the first value of the first 13, and the weight going from the first 13 to the to the first of the 16 was 1, then the full 1 would go all the way to the, and it might also go upwards as well. What did you say?
Or it could be like 5, right? In which case that one
Sure.
would multiply by 5, right?
And then it could also have a bias, which is where you adjust. That's like it's like a fixed constant or whatever that you're adding or subtracting in addition to multiplying whatever the inputs are.
And by the way, there are all kinds of like more interesting structures you can put in here. This is, as far as I can tell, is the simplest one, which is fully connected all. But there are ones that are like convolutional 2D things that have to do with like a 2D graphics, or like there's like a thing called dropout, which will like randomly remove a bunch of edges from these things. And there's like a you can have ones that are like internally cyclically connected that are like recurrent or whatever. And so there's some magic in like which ones do you pick. So I try to pick the dumbest one just to get started.
Because dense means fully connected.
Dense just means fully connected. Yeah.
And so then the idea with the training of the model is that you're going through a series of operations to figure out what those weights and biases should be for each node.
So we can do that. So now we say, okay, we're going to make a model. Here are the inputs, here are the outputs, and here's its name. And then you say, okay, I'm going to optimize it using the Atom algorithm. I picked it because, well, you can guess why I picked it, but I have no idea if it makes any difference which one I pick. And then I say, here's what I want to optimize for when I'm adjusting the weights. And so this is saying, I don't fully understand, but this is saying, this is categorical, meaning that this thing corresponds to some category. Cross entropy, which I don't know, it's a thing. And then sparse means, in the same way this was a sparse input, this thing will then produce for me a sparse output.
Okay.
And then from logits, this means how does it interpret the values in this last layer? The default was these values had to be between 0 and 1. And logits is some other way of interpreting true and false that goes from negative infinity to infinity. When I didn't have this, the thing blew up and got mad. So I put this in. There's an example. And then it says, while you're doing this, I want to report on how accurate this is. This just prints it out. Then I load in the data. And then from the data set, I extract the dealer's hand. Okay. And then I extract the 0th bid in the bidding record. I convert that all to tensors. And I shuffle the data set.
And what is a tensor?
A tensor is these. So the thing is called TensorFlow. So tensor is like the central concept in this thing. And so tensor is just a n-dimensional vector. It's like a matrix is like a 2 tensor, and like a cube full of floating point numbers is a 3 tensor.
I see. So we're using single tensors.
So we're using one-dimensional tensors because, I don't know, we're cave people or something. So then what I did is I said, I'm going to hold back 1,000 of my data points to test with. So I'm going to train on everything except the last 1,000. And then I'm going to validate my model against the last 1,000. And I say, okay, please fit the data. And then I say, now that you fit the data, please check on these ones you didn't actually get to see how you do. And we can run this.
Sure. Show me the money. Is it stuck?
I don't know. It's dramatic.
Did you click run or something, or is it just?
I clicked the run button. I think it's running down here.
Oh, okay.
Maybe I should have put a print earlier. And yeah,
okay, it's loading up a bit. Oh, there we go.
So it says this is the summary of my model. So this basically shows you the shapes as they flow through, and then shows you here are the parameters at each layer. So in total, there are 2,000 floating point numbers, 2,500 floating point numbers that can be trained. So now it's reading in the data. Okay, it's done.
This TensorFlow binary is optimized with one API deep neural network library.
Whatever that means. So now I told it to go try optimizing itself 10 times. So the first time through, it took 7 seconds. It was 50% accurate.
Okay.
But I think randomness, by the way, is 50% accurate. And so the second time through, it got up to 73% accurate and 75% accurate. So it's getting smarter. And it's going to top out here at about 70, 76 or 77% accuracy.
And this is the whole idea of like gradient descent, where gradient descent is like a fancy word for like finding min-maxing along some continuous function or continuous space, right?
Yeah, so that is, as far as I can tell, is the central idea in this branch of machine learning is you can put any kind of function together you want, as long as you remember how to take the derivative of that function for every parameter. So that basically means you can look at your loss function, and for each parameter, you can decide which way should I nudge this parameter to optimize my loss function.
And how is
And
loss computed?
Loss is that categorical cross entropy thing.
And that, I see. So that's the thing that we have to be minimizing. Really, what we want to be minimizing for is like difference from the correct bid.
Right. So when I tell it to go fit, I supply not only the hand as input, I supply here's the output that I think you should get.
Yeah.
And so it runs through all these floating point calculations and then compares using this loss function to the thing that I presented as the right answer. Now, of course, because these are human beings bidding, it actually, for the same deal of the cards, different human beings will bid different things. And so it's probably impossible to get to 100% with any given function because there'll be just contradictory answers.
And is that what the from logits allowed you to do, is to have contradictions in your data?
No, the whole design of this machine learning setup, the deep learning setup, allows for contradictions. Because unlike previously what we did before, where we used a SAT solver, where things were either true or false, and when you got a logical contradiction, all your logic formulas exploded. And in the previous system, the bidder would produce none. Like, I can't figure out what to bid now. You've confused me. So in this world, because everything is floating point, it doesn't care. And it'll just give you a low confidence answer. It'll be like, I don't know, maybe you should bid 3 spades. Maybe you should bid 2 ducks,
Yeah.
Anyway, so this is done. So it got to about 78, which is pretty good. And then you can then, against the test set, so it didn't get to see the test set in training, it also got to about 80%.
How good do models get? Because, I mean, 1 in 5 is really pretty terrible.
So in the tutorial, they're doing a classification of these like images of different things you can buy in a store, and like which one is a shirt and which one is a shoe, and it gets up to like 98% accuracy or something.
Wow. Okay.
So I think if we had a cleaner data set, like if we had a data set where all of the bids were made using a consistent approach, probably could get, I don't know how far we could get, but I would guess the high 90s.
Okay. I just look at this approach and I think there's so much promise here. So the SAT solver one that we did was actually like the 3rd approach that we've done to this, because we'd in the previous years written some other sort of expert system style, bidding helpers. But they all had the same problem, and the SAT solver was better in some ways, but again, they all bottomed out in the same problem, that sometimes you would just go off the rails and the bidding helper thing that we had written would just start saying, I have no idea.
Yeah, so this is the opposite. It's always going to say something. So the last step, by the way, of that script is it saved out the model to disk. And so this is a different file, but is now like the execution, or like now I'm going to use this in my program, right? So I load in the model. I stick another layer at the end, which is like, give me the max. Tell me which bid it thought was most likely. I shuffle the entire deck, deal myself 13 cards, and I basically ask the model to please predict me a bid, and then I go and print them out. So if I run this, this will...
so this is basically just like hand testing the model, looking at it.
Yeah, like just dealing some cards out, looking at it, just sort of look at like, does this make any sense?
Yeah.
I don't know why my machine is so slow. I think it may have to do with the fact that the video is overloaded.
The poor machine is trying to send two 1080p streams at the same time.
Yeah, so a bid out of like 100 hands. So if you know bridge, then let's look at, I don't know, what's an exciting bid to look at.
I find this way of writing out hands super non-intuitive. Like, I always expect the Yeah, I don't know. I just the spade ace, like that one you highlighted, is spade ace, spade king, spade queen. I don't know. It's just not how my brain reads it.
Yeah, so you like a common way of doing a bridge opening is you'll count the ace for 4, the king for 3, the queen for 2, and the jack for 1, right? So this would be like whatever this is, 9, 11.
I see 12 high card points, I think.
Oh, here's another ace.
Oh, there's an ace there too. So that's going to be
15,
16.
18.
What?
So 7, 14, 18.
It's where's that? You got
Ace, king, queen is
that's
9.
Yeah.
Plus an ace is 13. So 16.
Yeah. So 16 high card points. One
Six
spade. Did you have 6 spades? That
spades.
seems reasonable.
Yeah, so this is a reasonable bid. Like whenever I spot check these and like use my knowledge of bridge, they're reasonable, totally reasonable bids.
So this is we had proposed this and just I've been busy.
It's a 4 spade bid. 4 spades is a really huge opening bid, but like it makes sense, right? Like look at the spade holding: 1, 2, 3, 4, 5, 6, 7, 8 spades.
8 spades, yeah.
And 6, 7,
You
9 high card points.
And even better, that queen is isolated, so you really only have 7 high card points. And that queen's dead, or probably dead.
Yeah, I would bid 4 spades with this hand. That seems totally reasonable.
Depends on what seat you're in, but what was I going to say? Oh, so one of the things we talked about doing, and again, I've just been busy this week, is wiring up our old system, which we have to get it building 10 years later, which itself is a challenge, to feed it to the system, because it knows how to build consistently.
So I don't have that set up on my machine.
I don't think we can get it set up today, but we can maybe come next week with it.
But what we do have here, if we want to play with this, is our old system was called Stacy Bridge. In here, we have a data set that was generated from our old SAT solver-based data.
Oh, really?
So if we look at one of these things, so the advantage of using this data set is it will be consistent.
So this is already done what we were talking about doing.
Well, this is it. Yeah. So this is another representation of a deal. It's a board number, and then it says in this board number, here were the bids that were made. So it might be interesting to feed this to the model, because all these bids will be made in a consistent way. It doesn't have like the human factor of throwing in random bids.
This would take a bit of typing to get done tonight. So we do have some Python code that knows how to turn that board number into a deal that we could pretty easily extract. We might be able to do it.
The other thing I could show is it was so those numbers are like I just made up the model, right? And what I found fascinating is if I was like, how much can I simplify this model? Like, what if I put an 8 here? Or right, and I ran this and said, okay, train this. And what I found is, at least for this problem domain, it really didn't matter what I put there. If I put like really big numbers and I made like hundreds of thousands of tunable parameters, then it would overfit. So it would get a really high accuracy score on the data that it had seen. But when I ran it on the test data that it hadn't seen, it would be back at that 78% accuracy level. So here, instead of 2,500 parameters to tune, there's only 760 parameters. But it's still going to get, it's not going to do as well. So when I tried this before, it gets about 76% accuracy. So a little bit less, but like it's still like a tiny, much smaller model. And my theory of this is when a human being is bidding in bridge, there's like a heuristic people use, or like a algorithm that people run in their head, right? And what is basically what we're talking about, what we're doing just then, where we're adding up the high card points, so certain point values for every like ace or whatever, and then looking at the lengths of the suits. And so if you have 8 floating point numbers to represent your hand, that means you can have the high card points and the length in each suit. So it's sort of, because bridge is a game played by humans, that needs to be understood by humans, it may not actually involve that many floating point numbers.
Yeah, could make total sense. So should we try to do some code tonight? I worry we're probably going to run out of time. Like things we could explore are we could try do not the first bid.
Oh yeah, you want to try that?
I have no idea how to do that, but we could try.
I don't know either, but I didn't know how to do any of the rest of the stuff either, like until like 2 days ago.
Well, let's try. I think adding the concept of bidding history. I don't know how you introduce any sort of like memory into a model like this, but being able to make a second bid, I think, is very powerful. Would change what we could do here.
Okay, so let's do it. So I did find a thing in TensorFlow called long short-term memory layer.
Okay.
And I think that this thing is basically trying, like the types make sense. So let's try to add that to our model. So let's go back to, I don't know, this kind of thing.
Okay.
So as input here, we need to provide, let's see. Let's just try a new thing that we're going to do. Put this aside for a moment.
Danae says,
yes.
You can try using sequential models like LSTM.
Yes, this is exactly what we're going to try.
And you could tell us when we're doing it wrong.
So, okay, so I'm not sure exactly what, we kind of somehow want to instantiate one of these LSTM layers.
Okay.
LSTM. Okay, and for the sake of our sanity, let's then try to output a legal bid. Now we need to figure out what are the inputs. So it needs a thing called units.
I'm just reading it right now, the docs.
Yep. So try to find an example of this, just to have the right like types for things.
Yeah, I just can't tell if I'm an outsider and thus I don't know the lingo, or if this section of the industry just hasn't like cooled, in the like primordial sense of the forming earth or whatever, hasn't cooled to the level where like we understand what parts are important and which parts are not, and what part we can like write in plain English versus,
Here are the examples from the doc. To give you a sense here. This thing, similarly, it takes a list of integers. So we have to figure out how to encode that here. I think we put none here to mean an indeterminate number of integers. And then I don't know what this 4 is, but let's try it. 4. 4 is the thing is called units. Positive integer dimensionality of the output space. Okay. So I don't know, 16 dimensions of my output space. Why not?
Okay.
Okay. And then what is return sequence is? Return sequence is Boolean, whether to return the last output in the output sequence or the full sequence. I think we see the last one. Return state, whether to return the last state. All right, well, let's do this. Okay. So then we want to output from that a bid.
What does it mean to return the last output? Whether to return the last state in addition to the output. What does it mean to return anything?
So I think this is like a, my impression of this is like a hash algorithm. So like when you think about like how is like SHA-256 implemented? You have a hash block and you feed in your input and it produces like state that it retains and then output for the next block. And then the next block you feed in the next bit of input and you feed in the state and then it produces that again. And so you chain it together. And then at the end you have both the output and also the state that it would use if it was going to continue the chain.
Okay. I wonder if it's changing the like literal list of things that it returns from this function, this LSTM function, right? Because this thing, when you make an LSTM, it creates a function, according to this example.
I see.
And then you call it, and then depending on what flags you called it with, that function might return one thing or it might return multiple things. Like in this example that you quoted, right? The thing, it returns a tuple of 3. Whole sequence output, final memory state, and final carry state.
I think let's not worry about that. Let's try using it in its default form. So this is like, this input is the, so now I want to merge this with what we had before. So this is like the history input, bid, past bids, input. So then I want to feed through this LSTM. Then I have my hand input. And inputs. Then I want to feed through my categorical cross entropy thing. I want to concatenate x1 and x2. What is axis here? Okay. It takes an input, a list of tensors, all the same shape, except for the concatenation axis, and returns a single tensor that is a concatenation of all the inputs. Right, that's what I want. The axis on which to concatenate. So I think I want to concatenate along 1. That makes sense. And inputs. This is bad. Oh, no, that's fine.
You're missing now, but yeah.
Okay.
Whoa, that's so wild. It's like clipping out your video somehow.
Okay, I want to throw in some dense layers here for fun. And I want to output a legal bid. I don't know if I did it right. I feel like I need to split, like the opposite of concatenate.
This is called a recurrent neural network. A recurrent neural network is a type of neural network well suited to time series data. Recurrent neural networks process time series step by step, maintaining internal state from time step to time step. We'll use an RNN layer, that's recurrent neural network, called long short-term memory. Just reading a tutorial here.
Yeah, so I think the problem that I have, or at least what I feel like is my problem, is I have more than one input to my model. So I need one input, and I somehow need to take like the first 13 of them and feed them through this category thing. Then I want to feed the rest of my integers through this memory thing, because I want them to represent my bids. So I need some way of taking TensorFlow, like getting 2 outputs. Like, how do I feed part of my output through 1?
Well, this is exactly what building these graphs does. What is the like? You want to just like you want like a merge layer or something like that?
Well, I found the merge layer. The merge layer is concatenate. But I need like the opposite of concatenate. I need like split.
Why do you need to split?
Because when I go here to say model, I need to pass in one inputs thing. So what I think I want to do is I want to pass in a list of integers, the first 13 of which I'm going to represent the cards in my hand, and the rest are going to represent the bid history. And so I think I want to take my list of integers, I want to pull out the first n of them and shove them through the categorizer, and the last n of them and shove them through the LSTM.
And is there a way to just like write a layer that's all it does? Like, can you provide a custom function for a layer or something like that? because that would be very easy. Like it's just you're just slicing, literally the method called slice.
Yeah, I think so. I feel like this might have come up in one of the tutorials. Maybe we should look at one of the tutorials. I can share this. So what I'm doing here is let me stop screen sharing that, and let's start screen sharing the documentation that I'm looking at.
There is a tf.slice.
Oh, okay. Is that what I want?
Extracts a slice from a tensor. I see tensors there. You said this earlier, but it's their fancy name for matrix.
Yes. But I don't actually have a tensor. I have a layer.
Okay.
Or at least I think I have a layer.
Tensor slicing. Is there a slice layer and split layer in Keras?
What does it
Try
say?
a Lambda layer. This is from 2015.
Oh, layer is Lambda. Okay.
This is a GitHub bug.
Function. A Lambda layer exists so that arbitrary expressions can be used as a layer when constructing a sequential and functional APIs. Simple operations or quick experiments. For advanced cases, subclass layer. All right, well, we can subclass layer. Okay, but this looks sensible.
But does it give you the whole of the inputs, or does it just give you, like, what is X here?
X, I would assume, is one element of my batch. So I think this is going to work.
Okay.
So I'm going to say Keras Lambda. So I'm going to give it the input. Oh, no, the input goes here. Input. Okay. And the operation I want to apply is TF split, probably.
There are a lot of comments on this bug, by the way.
What?
Oh, there is a Keras backend slice, backend utilities.
Let me go back to screen sharing the code that I'm writing. So now I want TF split, I think. I think I want TF slice.
There's just a bajillion comments on this.
Size or number of splits. Okay. Then it splits a long dimension into size num or size smaller tensors. No, I think I want slice then. We did there a bajillion comments. What are the comments on?
On the, like, where's the slice layer for Keras?
Yeah. Okay. So either that means this is a common thing that everybody wants, or we're doing it wrong, and there's a reason why it doesn't exist.
I suspect it's both. I think it's just a common thing for us noobs to want. And
if you were an actual pro, then you wouldn't want this.
Yeah, you would think about the problem differently. That's what this smells like to me.
13. And then can I give it unbounded size? I'm not sure what size I want. I want like a none. I don't know. How many bids can there be? 10 bids? 13 bids for fun. Okay.
It's just a whole new world.
Okay. I did something.
Yeah.
This let's just make this 10. This number here is the place I'm least sure. Like I want a split that's like the rest. Like
Why do you even need a TF split? Because it's a tensor. It's not just like a list that you can't just like do -10.
correct. This is all so that it can record everything you're doing and then compute fancy derivatives of it.
And throw it on a GPU or whatever.
Yeah. But maybe I don't need these. Maybe I can just do. Maybe I can just do this. I think I can just do this. 0 to 13.
Oh, size is -1. If you do -1, it includes all remaining elements.
Great. -1.
Input,
Fold.
comma, begin, comma, size. And -1 is the magic that does all the rest.
The magic of doing everything. Okay. Okay. Seems like a thing. Okay. So then I'm going to just delete all this because we don't need any of this anymore.
I can see why people find this domain interesting.
I think what happens is you noodle around. Oh, did we read this? Maybe use the output of the LSM at each step and predict bids at each step instead of concatenating. I need to feed both the hand that you have and the bid history. The thing I was struggling with is how do I give the model both the hand and the bid history?
Well, what if you ended up like, would you run a model that would just like, because we think about it in this like stepwise fashion that like somebody runs a model inside their brain and produces a bid output, and then there are 4 separate models running, right? And each take their turn. But the input to any given model is what the previous 3 models did. And here I'm using model and like humans interchangeably.
Yeah, so you could imagine trying to predict the entire bid sequence at once. So I think, so now instead of first bid here, oh no, so this is like gen input. I want to take the whole, I want to do this for the dealer. I guess I want to do it for everybody, right?
Sure.
Okay, so this is like for hand in hands. And also for every hand, I want to look at every board. And then I want to look at for each bid in.
Well, for a given input.
Yep.
I think for a given run of the model, you want to do it for one specific seat. So you want like gen.
This thing really wants to like vectorize and do everything at once.
Okay.
I want to yield a hand. So I'm going to start with input string, and then I want to say input plus equals encode hand.
Wow, we went from 30 minutes to 58 minutes in the blink of an eye.
I definitely need to start writing code. I don't know if we're going to fully get this, but we're going to. Because you want to encode map encode bid over this.
Because what this will allow us to do is will allow us to predict a bid that are even not just the first bids.
Well, it allows us to predict the whole sequence.
Or a partial sequence from...
like the next step of the sequence, right? Gen, expected. The same structure here. And what I want to do is I want to... this is really -1 because I can never predict the bid after the last one. So then for each of these things, I want to return or yield code bid. 5+1. I'm trying to guess the next one.
Is your gen input supposed to return something?
Well, I need to yield the
Yield the input.
okay. And I think I can leave the rest of this the same. I'll try running it. I have no idea what it'll do.
Sure. I saw a bunch of squiggles, so I don't know that it will run, but
It'll probably blow up. So sorry that we're using my very sad machine that cannot both broadcast and screencast and learn machines.
well, you'll have to watch the show because the artifacts are really amusing. It
Oh no, it has no attribute lambda. That really threw a wrench in our whole plan here.
It's okay.
It's layers lambda. That's why.
They also the Stack Overflow folks gripe at you like, no, you shouldn't use Lambda. You should subclass layer instead. So
maybe that's the real answer. Is I should be subclassing. I should make a custom layer, or like you can just make an entirely custom model. You don't have to use any of this stuff. But I'm too dumb for that.
Well, subclassing layer doesn't look that hard. It's just like a couple lines of code, but
len is basically like overriding the main function in the subclass.
I think so.
Yeah. Call arguments received by Lambda Layer
to a tensor built-in function. That looks like you didn't call the function. You just returned it in your Lambda.
Okay. Calling layer lambda, type lambda, attempted to convert a value built-in function input with an unsupported type, class, built-in function, or method to a tensor.
Is lambda x? Is that
for reasons I don't understand? Sometimes you have to call this function. Or is to a tensor.
That to me read like x was a function that you were passed in a function, and that TF split was like, but maybe I.
Oh, it was TF split the thing that's mad?
Attempt to convert value built-in function input. So built-in function input. So the input function happens to be built in. Oh, go back. If you go up to the top, it's inputs, not input. And so input is
oh, that's an actual Python thing.
Correct.
Okay, that
was our problem in life.
That was a bad problem in life. I also wish that this thing was done in a language with type checking. That's like help me.
I thought modern Python had some type checking, doesn't it?
Maybe I'm not using it right.
Exception counter when calling layer lambda, type lambda.
Okay.
Adder num split.
Pass 0. I totally passed 0. Less than minimum 1. Okay, I'm pretty sure.
Split?
I think I could just do this. I think tensors have like indexing on them.
Great.
Let's try this instead of this split function.
Anyways, you'll be amused at the recording because every once in a while the screen flashes black and then paints like just your cursor and like a few pixels around it and then comes back.
I really apologize for all of that. Next week, maybe we'll tech up your computer to actually be functional.
Oh, yeah.
Then we can have the high quality streaming experience that you've come to know and love.
Especially now that I can size windows correctly. Is it running? What? Shape?
Okay. Yeah, so this is what happens when you plug in layers that don't actually fit. Input 0 is incompatible with layer. Expected 3 dimensions. Found 2 dimensions. Okay.
Why is this all in Python?
And why is it so hard to do? Sorry, so we gave the wrong shape of a tensor. We gave it a tensor that only had 2 dimensions when it wanted a tensor with 3 dimensions. So I don't know what the third dimension is supposed to be.
Do folks do ML in languages other than Python, or is it just all Python?
Python is by far the dominant one, I believe. So it looks like TensorFlow supports Python, C++, and Java. There's also a more button. I'm terrified to click the more button.
Is it
Okay.
just TensorFlow and PyTorch?
Oh, okay. Here it is. Here's the shape. The shape is supposed to be a 3D tensor with batch, time steps, and feature. So what is feature?
Anyways, I should say we're 5 minutes over. So if you don't think we're close,
I don't think we're close. We still have not really understood what this LSTM thing is. But you know, you're getting a flavor with it. So like basically this is what I did before is I fought with it enough so that all the shapes fit together, and then boom, it trained a model. And so basically once you get this thing to be happy and like plug in the floating point numbers together in shapes that fit, then it'll like learn something. And then you can see like, did that make bids that made sense?
Well, I enjoyed going on a TensorFlow journey, or at least observing a TensorFlow journey. But yeah, I think there's a bunch of cool stuff that could be done here. So, well, fun as always, Dr. Barth.
Do you know next episode is episode 100?
Oh my goodness.
Oh my goodness.
We're going to have cake and a party.
Yeah. Tune in next week to see what exciting thing happens for episode 100.
More of the same, Pinky. More of the brain. I don't know. You're probably the brain. Anyways, have a good night, all.
Thanks for joining us. See you next week.